So hello, everyone. Good to see you. So today in this colloquium, we have Professor Louis and from Cornell University. He received his PhD at Cambridge with a thesis entitled Extreme Point Methods for Infinite Linear Programming in '87. Then he moved on to Waterloo and afterwards to SFU, and he's been a full professor at the School of Operations Research and Information Engineering at Cornell since 2004. He's received various awards for his work, including Sime Fellowship, the Lagrange Prize, and the Eisenstadt Prize, to mention something local. But many more awards, and he's certainly considered one of the world leading experts in continuous optimization, variational analysis, with the various papers which received prizes, and well-cited monograph co-authored with John Borwein, which is entitled Convex Analysis and Nonlinear Optimization. And today he's going to talk about connections of variational analysis to ever-current deep learning.
Great, thanks. Thanks very much, Tim. Is my sound okay? Sounds all right, great. Bon, donc évidemment, je vais parler en anglais, mais il faut dire que je suis vraiment désolé que je peux pas être chez vous, especially for the dinner that you guys probably owe me for speaking. So and as Tim said, there's this nice, I would like to imagine myself speaking the Pavillon Eisenstadt, and in celebration of that connection that I had, and it's too bad that I can't be there. But anyway, I miss you guys. Et s'il y a des questions en français, je serais content de répondre en français. Voilà. Okay, so this talk is actually, this is the kind of talk that would be much better as a Blackboard talk. So this is sort of a fake slides talk. So it's going to be completely bereft of any fancy pictures that would normally go with this kind of a talk, and it would actually work really well on a Blackboard because it's kind of in some sense it's sort of a one-liner. It's based on a very short paper. But it's a paper I really like, and it's a one-liner that I really like. And in fact, the one-liner is kind of curious too, because it's really a one-liner about what I think is a beautiful idea, not of ours, that kind of doesn't go anywhere as it turns out. But it's still a beautiful idea, and it gives me a great excuse to talk about lots of other beautiful things that are connected with it. So it makes a nice story. So that's a story I kind of would like to weave, if you like. And I think the result is a nice result too. So just imagine me writing on the board. Okay, so in broad outline, there's a lot of words here. So let me just give you an outline, the direction that I'm going to go. So I want to, in some sense, be motivated by the kind of practical optimization that happens in machine learning, deep learning. So it's a very, very large scale optimization, which, by the way, I don't do. But it's good to be informed about, and that, how does that work? So that works using subgradients, basically gradients or subgradients, and so when one tries to see what happens with that method, one runs into. Oh, let me say, by the way, if anybody wants to ask questions as I go along, I'll try to keep an eye on the chat. So if you do want to throw questions out, feel free, or just interrupt verbally too. That's absolutely fine. You quickly run into problems that are not smooth. So the classical subgradient method for convex optimization is in some sense designed to deal with non-smooth functions. So that's very classical. So I'll talk just a little bit about that. You also run into problems that are not convex, and that's a sort of a more recent challenge that people have tried to think about. So very concrete problems in sort of deep neural nets, if you like. The kind of objectives that you're looking at aren't necessarily convex. And so the kind of line that I'm going to follow is a very beautiful paper, a fairly recent paper by Dave McDavis, Dmitry Druzhatsky, and Kakade and Lee, So I'll be very kind of motivated in describing their kind of approach to that problem. And then there's a sort of a third ingredient which they considered less, which is that very often in machine learning kind of applications, the kind of software suites that they use, they're really not coding in the kind of gradients and subgradients in any kind of hardwired way. They're doing it via automatic differentiation. So there's some kind of automatic or algorithmic differentiation routine running in the background that you don't even see, and is spitting out, what you hope are gradients or subgradients as you go along. And so that creates a, another layer of sort of vagueness as to what's happening with these algorithms. So I'll talk a little bit about that, and about how that guides you in various directions that variational analysts have thought about for a long time. So different ways of generalizing the notion of the gradient of a function of several variables, where several means several million probably. So and the two kind of directions that I want to talk about there, so that there's, again, this is a nice local connection, because Francis Clarke was director of the CRM actually for, from the late 80s onwards for, I guess, 8 or 9 years. And this was sort of a decade or so after his thesis, where he sort of came up with this original notion of how to generalize the gradient of a non-smooth, non-convex function. So I'll talk a little bit about that kind of direction of generalizing gradients. And then this more recent idea that again, a very recent paper of Jerome Bolte and Bolte and Pauwels wrote in last year, pretty much, on a kind of different way of generalizing the idea of a gradient based around conservativity kind of aspects of the gradient. And I'll talk about the connection between those two ideas, and how they relate to these subgradient descent schemes, roughly. And then what I want to do is sort of draw those two ideas together in a concrete, in a sort of a concrete world, the world of semi-algebraic functions, semi-algebraic objectives, which most objectives in real life are, and talk about how stratification kind of ideas can sort of give us a view on how these different ways of generalizing the gradient give us a similar kind of understanding of what's happening with these optimization schemes, why they're working. So that's the sort of broad picture that I'm going to follow. Okay, so so let me then just start by talking a little bit about subgradient schemes for solving large-scale optimization. So these are, the fundamental workhorse of modern optimization as it applies to machine learning, so at very, very large scale. So, the basic workhorse is this notion of the stochastic subgradient method. I'm not really going to talk about the stochastic aspect of this very much, except to give you the framework. So how does it work? So you're trying to minimize some function of some large number of variables. And a typical scheme, a typical stochastic subgradient scheme, is an iterative scheme which iterates in the following way. So the xk is your current iterate, and you update xk by moving, some predetermined step, and it's usually, something like 1 over k. So something for which the sum of those things diverges, but the sum of the squares converges. So something like that. Times some direction yk, which is kind of a subgradient, and then some noise, and then there are some restrictions on what the noise is allowed to be. So typically that's kind of mean 0, and some control on the variance. Okay. So yk here then is a gradient if the function's smooth, or it's a subgradient at the current iterate. So you sort of imagine you've got some oracle that gives you that, or it gives you maybe some approximation of it subject to some random noise, maybe because you've only sampled some random bit of your function that you're looking at. Okay, so psi k is mean 0 noise. Okay. So then so the question is, what do we know about the convergence of these kind of schemes? And in particular, when can you guarantee? So the weakest kind of convergence result that optimization people really hope for as a bare minimum is that if you find a limit point of this sequence, then it should be critical in some sense. Okay, and I'll come back to in what sense in a moment. So what guarantees that sort of bare minimum of some kind of convergence of this optimization scheme? What guarantees that if you've got some convergent subsequence, then the limit point is a critical point of some sort? So what do we know about that? So this kind of scheme goes back a long time, 70 odd years. Robbins-Monroe originally came up with, I think they called it stochastic approximation or stochastic gradient descent, we tend to call it now. So that's as it applies to roughly speaking, smooth functions. And then there are various complexity kind of results. So the convex case, when the function you're looking at is convex, that's the classic subgradient method that Nemirovsky and Yudin analyzed 40 odd years ago and gave a complexity analysis for, so in that convex case. In the smooth case, so without the convexity but with smoothness, the complexity there is quite a bit more recent. So there's a kind of pretty comprehensive paper by Gadimi and Lan doing the complexity there. And then, if you have neither, but you're what you might call weakly convex. So for our perspective, you can think of a weakly convex function as just a sum of a smooth function and a convex function. So if you look at that case, then what happens? Well, then the analysis is really quite recent. And really even convergence, we only really knew fairly recently from this paper. So this kind of result is that the limit points are almost surely critical. And so if there's no stochasticity, they're critical. And furthermore, the function values converge. Okay, so you get convergence in function value. So you get that kind of result. Okay. So that's kind of nice. So again, weakly convex for our purposes just means sums of smooth and convex functions. But then you kind of so you kind of sit back and you think, well, that's an advance, and then at some point you realize that, but actually when you look at common machine learning type of objectives that you see in deep learning, they're actually very often not weakly convex. So they don't have this nice property of being the sum of being expressible as the sum of a smooth and a convex function. And so you kind of run up against a wall at that point, because the existing theory, even the existing theory up to 2018, didn't really cover that situation. All right. So so that leads me to start to talk about Clarke subgradients. So these are activation functions that appear in deep neural networks when you're applying it in these big machine learning applications, deep learning applications. They are given to you as a bunch of ingredients, and those ingredients are often not weakly convex. And just to give you a very, very simple example, a toy example of a function that's not weakly convex, minus the absolute value of x, right? So minus the absolute value of x is not a weakly convex function. You can't write it as a convex function plus a smooth function. But functions that look roughly like that often appear as ingredients in the kind of thing that you're trying to optimize, embedded in various layers. And so then the question is, well, what do you do? And so one thing you can think about is that these functions that you are applying it to are at least Lipschitz functions. And Lipschitz functions are at least differentiable almost everywhere. And so that gives you access to a kind of a generalized notion of a gradient, which was the notion pioneered by Clarke in the 70s. So you could think instead about working with Clarke subgradients. So these are elements of what I'm going to call the subdifferential. And what is the subdifferential? So the subdifferential is a sort of a generalization of the corresponding notion for convex functions, which in this Lipschitz setting, you can think of as convex combinations of limits of nearby gradients. Okay, so you look nearby, you look at what the grade, look at nearby at these, this full measure set of points where the function is differentiable, take limits and then take convex hulls of those limits. And that gives you Clarke's notion of the subdifferential. Okay. So that gives you a nice object to try to work with. And what even more recently this beautiful paper by this quartet of authors showed is that for nice functions, So I'll use the word tame, and I won't really talk about what tame means, but in particular, if you want to think about semi-algebraic functions, and this I will define later if you don't know what that means. So, but sort of roughly speaking, concrete functions, the kind of functions that are concretely represented on a computer, then if you look at limit points of the stochastic subgradient method, where by subgradient you mean Clarke subgradients, these things, you do get this convergence result. Okay, so they showed that the limit points are critical. And by critical, I mean 0 is a Clarke subgradient. Okay, so critical in that sense. And you also get convergence in the function values too. So that was like a beautiful advance, really quite dramatic. So what's the step size here? Yeah, so again, a kind of a predetermined sequence of reducing step size kind of things, exactly. Yeah, I'll just keep the chat open there. Okay, so that's good. And by the way, I should emphasize these kind of methods, you can't, you need a predetermined sequence of step sizes because you can't do any kind of line search sort of things, okay? Because it doesn't make any sense to do a line search because, for example, you might not even be moving in a descent direction, right? So there's no criterion, even supposing you could do it, there's no criterion to search for. So you just pick your predetermined sequence of steps and go. Okay, so that's great. So that was nice. But then again, you kind of run into a problem because it turns out that when people actually apply these things, and this was my sort of rather bad-tempered abstract saying, these people just apply it, and like it's really annoying, right? Because when you actually apply it, these big deep learning solvers, as implemented by Google or whoever, PyTorch and TensorFlow, they use these gradient-like directions that actually turn out are not Clarke subgradients. Okay, so it turns out they're somehow producing these gradients that really aren't subgradients. So these gradient-like things that are not actually subgradients. So that's kind of weird, right? So this result really doesn't work in this sort of setting because you're not looking at Clarke subgradients. And so I just want to sort of explore that a little bit because that's a little bit curious and a little bit surprising. So let me just tell you what they do produce, just give you an example. So what they do, these things, at least as applied with automatic or algorithmic differentiation, so they don't try and code what the derivatives or what the subgradients are. Yeah, so depending on whether you want to go up or down, I mean, that's a good question, so and that of course has to do with whether the functions got convex-like properties or concave-like properties or what, right? So good question, because there is a certain symmetry there, right? So the idea is you're moving in a negative gradient direction, whatever that means. Okay, so the negative gradient direction tries to generate the descent. Okay, that's roughly speaking the idea. Okay. So some negative gradient-like direction. Okay, so how does automatic differentiation work with these non-smooth ingredients? So, as I said, these packages, PyTorch and TensorFlow, they often produce kind of surprising results. And so let me just show you a kind of a toy example. So this is an example from Bolte and Pauwels. So if you feed this particular function into TensorFlow, one of these solvers, where you're just taking the positive part. So, again, what I want to emphasize is what happens with automatic or algorithmic differentiation is that the code itself is in some sense being differentiated, right? So you're not really differentiating the function, you're really differentiating the representation of the function in this algorithmic way. And if you happen to represent this function in a particular algorithmic way, where this is the ingredient, then what comes out is the following gradient map. Okay, so whenever you put in a non-zero number, you get 0. But if you put in the number 0, you get 1. Okay, so this is a perfectly simple non-smooth function. You can feed it into TensorFlow, and this is the answer that it gives. But if you look at what that function is actually identically 0. Okay, so this function, the function f of x as a function is identically 0. And yet when you feed it in, you're getting this weird looking gradient, right? So it's sort of very curious. So it's not that the function itself is non-smooth and you're only getting one subgradient. This is not a Clarke subgradient that you're getting here, right? So what it's spitting out at 0 is not a Clarke subgradient. So that's a bit disconcerting, right? So what does one make of that? And so let me just say, so even though automatic differentiation, it produces these gradient-like things, what it thinks are gradient-like things that are not Clarke subgradients. And even though, so you know, one other way you might think about this is, well, I just told you that Lipschitz functions are almost everywhere differentiable. So maybe if you just kind of randomize it, the chances of hitting one of these weird points is 0, and so you don't have to worry about them, right? But it turns out that argument is sort of fallacious as well, because the way that these things are coded, they're kind of layered, right? And so they've got these layered ingredients. And when you look at those ingredients, they often get evaluated at points where they're not smooth. So you really do hit those non-smooth points, however, you know, whatever you're doing with your algorithm. So they often return gradients of the ingredients that are evaluated at non-smooth points. So it's not like you can sort of pretend the function is smooth just because Lipschitz functions are almost everywhere differentiable. So something, you know, something more subtle is going on. And yet, despite all that, they work, right? Which is really annoying. So annoying to variational analysts, right? So that's the sort of dilemma. Okay, so they work. So the question is, what, you know, why are they working? Okay. Let me just pause and see if there are any questions. So really kind of get the broad picture. Okay. Great. Okay, so Bolte and Pauwels actually in this beautiful paper, they gave a nice explanation of this. So basically what they did is they showed that, you know, when this automatic differentiation routine goes on, it produces this gradient-like map that it's not a Clarke subgradient, but it does satisfy some nice calculus. It's got some nice calculus. And in particular, it satisfies a kind of a chain rule. And here's the chain rule that it satisfies, that if you look along any trajectory, so, and I'll define this a little bit more carefully later. So if you look along trajectories, then the natural, and you compose, you know, where you are on the trajectory in the iterate space with the objective function, and you look at what happens, the time derivative of that, then it satisfies the right chain rule. Okay, so you get the inner product of the velocity vector with the gradient. Okay, which is exactly what should happen, right? So that chain rule holds almost surely. Okay, so for all trajectories, you get this nice chain rule happening. And that chain rule actually is enough to prove the convergence of the method. So that really gives you a convergence technique, a convergence proof technique that enables you to, it basically imitates the approach of Davis and Trusviatsky and Kirkade and Lee. Okay, it's a Lyapunov kind of argument. So there's a Lyapunov kind of technique that sort of evolved over the past couple of decades, which shows that uses this kind of chain rule as the fundamental tool to get yourself where you're going. So these are various fairly recent papers and in particular this fairly recent paper of John Ducci and Rowan from a couple of years ago, very much pioneered this kind of Lyapunov stochastic subgradient convergence proof. Okay, so that's sort of the explanation. So the explanation is, okay, they're not Clarke subgradients, but they have a nice chain rule. And that's what really matters. What really matters in this kind of framework is the chain rule. Okay. All right. Okay, so that sort of suggests that in this setting, at least, maybe we're looking at the wrong thing. We shouldn't be looking at Clarke subgradients as this notion of gradient-like objects. We should be looking at things that somehow satisfy a chain rule type property. All right. And that led Bolte and Pauwels to suggest a different kind of approach to thinking about generalized gradients. They said, well, okay, maybe we should think about generalized gradients that satisfy the chain rule, right? That we use that as a definition. Okay, so what gradient-like fields satisfy this sort of chain rule? So they proposed the following idea, which was a kind of a beautiful idea. They said, okay, you know, if you want to think about convergence of subgradient methods, which is a really pretty fundamental question, then let's define a new notion of a generalized gradient for Lipschitz functions. And it's basically that the chain rule should work. Okay, so how does it work? It says, okay, I'm going to think about what I'm going to call a conservative field. So a conservative field is a set valued map. Okay, so it's an operator, so it goes from Rn to Rn, but Rn to sets in Rn. So it's a non-empty set valued operator G. It's got some, a couple of technical conditions. So it's got closed graph and it's locally bounded. And and when you select from it, the chain rule should always hold. No matter how you select, the chain rule always works. That's the idea. Okay, so all absolutely continuous curves, so integrals of indefinite integrals of integrable functions, satisfy the chain rule. Okay, so they satisfy this chain rule in this sense. Okay, so for all absolutely continuous curves, this chain rule should hold almost always, no matter how you select this gradient-like thing from the gradient field, from this conservative field. All right. So that's their definition. And it turns out that in practice, so when do these things exist? So in practice, these fields usually exist, and when I say usually, I mean always, right? So essentially always. And in that case, you call a function that does have one of these conservative fields path differentiable. So if it's got one of these conservative fields, it's path differentiable. And this sort of notion again is an old notion, viewed at from a slightly different perspective that goes back to the French literature in the the late 1980s. And in particular, it's true. So in particular, it's easy to check for smooth C1 functions, convex functions, sums and differences of these functions, these kind of functions it's going to work for. And it's also true in the case that I'm going to be particularly interested in, which is semi-algebraic functions. Okay, so semi-algebraic or more generally, so-called tame functions, so a sort of generalization of what semi-algebraic functions are. All right, so then what do these things look like? What do these conservative fields look like? So we're coming at it from a very, very different perspective than Clarke, I guess. And so what can these things look like? That's the question that I want to pose. All right, so Tim, when should I aim? How am I timing this? Am I aiming at 4 or 10 to 4, or what am I doing?
I think Jessica knows best.
Oh, Jessica, right. Jessica, order me around.
Maybe let's say 5 to 4.
Okay, great. Sounds good. Perfect. Great. Okay, so what do these things look like? That's the question. So again, you got one of these nice closed, locally bounded, non-empty set valued mappings, operators that satisfy the chain rule. So what can they look like? Okay. So the first thing that, again, this is something that Bolte and Pauwels observe, is that if you have one of these path differential projective functions, so remember, a path differentiable function is one that does have a conservative field. So there is at least one conservative field that works out there for this function. And in that case, the Clarke subdifferential itself is one that works. So if anything works, then the Clarke subdifferential works. And in fact, it's minimal, it's the smallest such thing, at least among those that take convex values. Okay, so it's the minimal, so among those functions that have a conservative field, the Clarke subdifferential is minimal. Okay, so you can't get any smaller. And usually that's a good thing for, variation analysts like that. They like minimality properties, essentially because Clarke's motivation when he was coming up with the idea of generalized gradients was writing down optimality conditions, right? And the smaller the object is, the stronger the optimality condition, basically. That's the idea. So minimal is usually good. But on the other hand, this automatic differentiation example suggests that, that we might be interested in other conservative fields, all right? And so let's look back at that example again. So for example, this operator here, which takes the value 0. So remember, it's set valued. It takes the value 0 for all non-zero points, and it just is the unit interval when x is 0. So if you think about that that's a closed, set valued operator. It's locally bounded. The values in it don't blow up. And it turns out that that is a conservative field for the identically zero function. So if you, whenever you look at a trajectory, the trajectory goes along, it sort of either crosses through x equals 0, or it lingers at x equals 0 for a while, and then goes out either way, but it doesn't matter, it still satisfies the chain rule. Okay, so this field is perfectly fine as a conservative field. Okay, even though it's bigger than the Clarke subdifferential. Now, it's not all that much different, right? It only differs at x equals 0. Okay, but still differs. Okay, so I guess the point that I'm making is these gradient-like things, Clarke's idea and this idea of a conservative field, they're defined and they're motivated very differently. So for the Clarke subdifferential, the motivation was it kind of grew out of convex analysis. And the idea was, or at least one approach to it was thinking about limiting gradients, and Clarke was motivated essentially by optimality conditions in the calculus of variations. Okay. So that was the sort of driving philosophy. Whereas here, for conservative fields, we're motivated very differently. We're trying to make the chain rule work. And why are we trying to make the chain rule work? Well, because we're trying to force through this Lyapunov argument for the convergence of subgradient methods. So that's the idea now. So very, very different kind of philosophies. And yet, at least in this example, the difference between them is actually rather slight, right? It just happens at one point. At one point, the answers are very different. Okay, so in practice, and we'll see more examples of this. So in practice, the distinction between these two ideas seems to be pretty slim. And so it's that kind of fact that I want to explore a little bit. All right, so what I want to do now is I want to talk a little bit about structural aspects, and so to do that I need to talk about stratification. So in particular, what's called Whitney stratification. So when you look at the concrete sets, and for us, concrete is going to mean semi-algebraic, and I'll tell you what that means in a moment. But these kind of sets that you see in real life, in these real world applications, they are finite unions of manifolds. So smooth manifolds. Okay, so what do I mean by, in our setting, again, just to be very basic, a manifold for us is just defined locally, and it just means that nearby the point that you're interested in, it looks like the solution of a bunch of smooth equations. So you've got some smooth equations, and their gradients are linearly independent. Okay, so you've got a bunch of smooth equations, linearly independent gradients, and at each point in the manifold there should be a representation like that. Okay, so that's what I mean by a manifold. Okay, and again, in real life, in these sets that we're going to look at in real life, they can be partitioned into manifolds. They stratify into manifolds. Now, there's this notion of the normal space to a manifold at a point x, and that is just the span of the gradients. Okay, so you get the subspace, which is the span of the gradients, and that's what differential geometer would call the normal space. Okay. All right. So what is a Whitney stratification? So Whitney stratification is a sort of a partition of the set that you're interested in. You've got some manifolds, they're disjoint. You look at their union, and you say that that's a Whitney stratification of the union if there's this additional, rather technical looking property that holds. So it's actually two properties, really. So what is this property saying? It's basically saying that if you've got a sequence of points that's converging to some point in some other manifold, then first of all, there's this sort of frontier property that says that manifold must be contained in the closure of the first manifold. Okay, so that's the first property, stratification property. And then there's this second property that basically says that is a sort of a closure property. So this, again, this is not usually the way that the Whitney stratification property is written, but it's sort of familiar from a variational analytic perspective. So if you look at a bunch of normals and those normals converge to something, then that something should lie in the normal space to this other manifold. Okay. And the nice thing about that property is that, so again, if you want to make this concrete in your mind, think about a polyhedron and think about decomposing a polyhedron, partitioning a polyhedron into its open facets. So, you know, the relative interior and the relative interiors of the faces. Okay, so that's an example of a Whitney stratification, exactly that. So there's, you know, so there's this sort of technical condition which you know guarantees that these manifolds are sort of interacting with each other the right way, and then there's this kind of closure property that we also have that is going to be useful in what I want to do. All right, so that's a Whitney stratification. So now one sort of elegant application of the idea of a Whitney stratification is to sort of generalize that example that I did that came out of TensorFlow right at the beginning, which is to think about, you know, if I give you the identically zero function, what do conservative fields look like for the identically zero function? And one very nice class of examples is what you might call the normal operator for a Whitney stratification. So how does this operator work? It just, you know, it says, okay, you're sitting at the point X, look around in this stratification for which manifold you're in. And if you're in this manifold M, then this operator spits out the normal space. Okay, so that's, you know, a kind of nice, well-defined operator because this stratification is a partition. And so you look for the manifold you're in and spit out the normal space. And then the Whitney property guarantees that this normal operator is closed. It's, you know, one way of saying it is that that normal operator is a closed operator. Okay. All right. Now, you know, it's basically a kind of like an easy little exercise in real analysis to see that operators that look like this, so the normal operator of a Whitney stratification gives you a conservative field for the zero function. All right, so again, if you think back along the real line, you could take a bunch of points on the real line. So let's just take a simple example. So if you look at this stratification of the real line into, you know, the strictly negative reals, 0, and the strictly positive reals, okay, that's a Whitney stratification. And what's the normal operator look like? Well, everywhere here, the normal space is just 0. Okay. So at every non-zero point, you just get 0. When you're at 0, you get the whole real line because that's the normal space to this manifold that just consists of a single point. And so you get this operator here, this normal operator here. Okay, and that is a conservative field for the zero function. Okay, so our, you know, that TensorFlow example that we did, automatic differentiation produces a gradient-like thing that comes out that is selecting from this field. Okay, so remember, it's giving you 0 everywhere except that it gives you 1 at x equals 0. And actually, you know, the nice thing about that is it's locally bounded too, which I've kind of brushed under the carpet. Okay, because that's an additional property that we want. All right, so okay, so just to summarize, Whitney stratification. So stratifications, the normal operators associated with them. So just, you know, spitting out the normal space whenever you're in any particular manifold, that gives you a conservative field for the zero function always. Okay. All right, now let me just be slightly more precise about what I mean by these semi-algebraic sets. So this semi-algebraic world, which, you know, I like to think of as a good model for concrete optimization, for optimization in real life. So the sets and kind of functions and operators that we think about in real life are all the kind of things that you can, again, finitely represent on a machine. And so what do they look like? Their semi-algebraic sets are finite unions of what you might call basic sets. And basic sets are those defined by finitely many polynomial inequalities. Okay, so you get this, you can have an arbitrary finite union of such sets. So that gives you a very rich class of sets that are not, you know, not particularly well behaved from the perspective of variational analysis, right? Because they're not, you know, they're not convex, they're not, you know, regular in a variational analytic kind of way, but they are very well behaved from many other mathematical perspectives. And in particular, the Tarski-Seidenberg theorem says that if you look at a linear projection of a set like that, it retains that property. Okay, so projections of semi-algebraic sets are semi-algebraic. So these kind of sets are very robust under many kinds of mathematical operations. And so in particular, for example, if you're interested in optimization, feasible regions of semi-definite programs, for example, are semi-algebraic. Okay, so you have this very, semi-definite representable sets are semi-algebraic. So you have this very rich class of sets that kind of model in a certain natural way the concrete world. All right. Now, so what has that got to do with what we were talking about? Well, they stratify. That's the key property that we're going to use. So semi-algebraic sets, you can decompose them, you can stratify them, you can partition them into manifolds, and you can do it in a way that satisfies that Whitney stratification property. And that's a sort of a standard fact of semi-algebraic geometry. Okay, so semi-algebraic sets stratify in the sense that we were talking about. All right, so we're kind of nearing the sort of punchline of this story that I'm trying to weave. So let me just talk. So the last ingredient that I need to talk about is the Riemannian gradient. So this is the sort of analog of the gradient of a smooth function, but now this smooth function is restricted to one of these manifolds. All right. So let's suppose that I've got a one of our objective functions, which remember is not smooth usually. Okay. But let's suppose that on some manifold it is smooth, so its restriction to some manifold is smooth. So then we could think about its gradient in a Riemannian sense. And what do I mean by that? So what I mean by that, again, just to be very elementary, is that there's some other smooth function that agrees with it on that manifold. Okay, so you can, if you like, extend it to a smooth function. Okay, so that gives you a sort of a concrete way of thinking about it. And then if there is, so if it's smooth on a manifold, so there is this kind of extension, you could think about the gradient of that extension and just project it onto the tangent space. And that's what we call the Riemannian manifold. Okay, so for a point in this manifold, the Riemannian gradient is just the projection of the gradient of any of these representatives, it doesn't matter which one, onto the tangent space. Okay, so you take the projection of this smooth representative, of the gradient of this smooth representative, you project it onto the tangent space. What's the tangent space? Just the orthogonal complement of the normal space. Okay, so the linear approximation to the set. All right. So that's the Riemannian gradient. And so, so that brings us to the kind of key tool that's going to drive the final result, and which is the following. So this is a sort of a combination of some earlier work that we did, a decade or so ago, and again this recent paper of Bolte and Pauwels that says the following. Okay, so it says let's think about one of these pairs of an objective function and a conservative field for it. And let's suppose they're both semi-algebraic. Then there's a stratification of Rn, the domain of F, into manifolds. And on all of those manifolds, the function is smooth. And what does this conservative field do? Well, it selects, it's a selection. So it's taking some subset out of some other operator. And what's that other operator? Well, it's just the sum of the Riemannian gradient and the normal operator. Okay. So, if you say, okay, well, what's the value of this operator at any point? You look at and see at what manifold are you sitting in this partition. You calculate the Riemannian gradient in this way. You look at the normal operator at that point, which is just the normal space to that particular manifold at that point. And what the conservative field has to be doing, at least, is it has to be selecting something from in there. Okay? It has to be choosing some subset of this. Okay. So that's the basic observation. And in particular, because we know by assumption that the Clarke subdifferential is one of these conservative fields, this is true when you replace G by the Clarke subdifferential, right? So in particular, that holds when you plug in G as the Clarke subdifferential. And that actually was the original result back in 2007. Okay, so it's basically saying the Clarke subdifferential, but not just the Clarke subdifferential, is selecting from the Riemannian gradient plus the normal space to this particular stratification. All right, so let me just pause for a second to see if there are any questions. How tight is this inclusion? Yeah. So, you know, so that's a good question. And it kind of depends, you know, it depends how, so for example, if you're an automatic differentiator, then, you know, you're selecting from this conservative field, which might be quite a bit bigger than the Clarke subdifferential, okay, as we saw. But it can't be too much bigger. That's the main point, okay? So in general, you know, this is not tight in particular because this in particular is not locally bounded, right? So again, I'm sort of brushing the locally bounded aspect under the table, right? Which is sort of complicating things slightly because this thing is not locally bounded. So you know, this is not exactly the right answer. It's just kind of giving you a local picture of what it looks like. So, all right. Okay, so we're now ready for the main result. Okay, so here's the final result then. So this is the result with my co-author Tonghua Tian, which will appear soon in SciOpt. So it says the following. So again, the same setting. So you've got a Lipschitz function on Rn and some operator, so a set valued mapping from Rn to Rn. They're both semi-algebraic. Then the following two things are equivalent. So one is the statement that G is a conservative field for F. So this is going to be, so this result is going to be a characterization of conservative fields. Okay, so it's going to say exactly what conservative fields look like. So one is that G is a conservative field. And the equivalent property is that it's just, you know, well, it has to be closed, locally bounded, non-empty valued, right? But it's just a selection from the Clarke subdifferential plus the normal operator. Okay, so it's as simple as that. So here, this is the Clarke subdifferential, and this is the normal operator to some Whitney stratification of Rn. Okay, so so if you've got a conservative field, it has to, of a semi-algebraic function, it has to look like a selection from the Clarke subdifferential plus, you know, what is really a conservative field for the zero function. Okay, so it's as simple as that. And so, you know, kind of when I said this is a one-liner, I mean that, you know, it's more than one line, but what it's really saying is that the distinction between the Clarke subdifferential and conservative fields is actually pretty modest, right? The distinction is in this normal operator. So there's some normal operator to a Whitney stratification which can get thrown in there, but that's the only difference. Okay, so in a concrete setting, gradients chosen from conservative fields, they're just slight modifications of Clarke's original generalized gradient. And so that's kind of the end of the story, and I will take questions. So.
Thank you very much, Adrian, for a very interesting talk. Are there any questions from the audience? Please feel free to raise your hand or simply unmute yourself.
So Adrian, excellent talk. This is Sean.
Thank you, Sean.
My question is, you see the function class you're talking about, how much they are different away from like a Bolte and Pauwels, they're talking about essentially smooth.
Right.
Lipschitz functions.
So that's a very good question. So there's, yeah, so historically, you know, if you go back to this work of, you know, Valadier, so let's go back. Where are we here? Yeah, this idea of path differentiability. And yes, so there was this, you know, this material that you've worked on exactly as a, you know, essentially differentiable. So I think it's almost everywhere strictly differentiable, right? I think that was the class. And that there is a slight difference. So the difference is slight, but there is a difference. And so but in some sense, you know, I'm kind of more interested in the, you know, the sort of concreteness of it. So this is the sort of key property that I want to focus on, the fact that semi-algebraic or tame functions definitely have this property, and they also definitely have the, almost everywhere strict differentiability property that Bourne and Moore studied. So yeah, but it's a good question. There is a slight difference with Valadio, but it's not huge.
Thank you.
Sure.
I have a quick question. Will Clarke regularity give you anything in terms of the tightness of the inclusion for a given conservative field and the Clarke subdifferential plus the tangent, the normal space?
Right. So again, it kind of depends a little bit what you mean by tight, right? Because in some sense, I think what you're striving towards is, how big could this be, right? I mean, how, the Clarke thing is the smallest in some sense. How big could the thing be? And that's a slightly difficult question to answer because, even on the line, for example, you could keep adding points to it and adding like a vertical line. And so it's a little bit difficult to make that question precise. What is true is if you have Clarke regularity, that's enough to make, to give you path differentiability, for example. Okay, so Clarke regularity does give you path differentiability. That's certainly true. Or Clarke regularity of minus the function. Both those are sufficient. So that's certainly true.
Yeah, I just thought of it because this decomposition of the zero function at the beginning, I mean, it was still, of course, it was a zero function, but it was a decomposition into at least one non-Clarke regular function, right? One of the summons, right?
Yeah, so it's slightly weird, right? Because the definition is only pointwise, right? So it's not like you're adding functions together somehow. So it's so if it's this function here, right? And so it's a slightly odd looking, it's an odd looking thing, right? Because the definition varies depending which manifold you're on, essentially. So it's not like you're adding, you're adding the indicator, you're adding somehow the normal cone operator for a fixed set. It's not quite like that, right? Because it's, that normal cone operator varies depending on which manifold you're in. So.
I have a question. Could we go back to the last stage, like the main theorem?
Yeah.
So maybe you mentioned this, but I didn't catch. So are these stratifications unique, or how they're?
No, so no, they're not unique, and in fact, again, if you think about the case of just the real line and the function being zero, you could stratify the real line in many ways, right, and keep refining it by adding points, and then you would get bigger and bigger examples of conservative fields associated with those stratifications, right? So there is no uniqueness in the stratification, right?
Okay, so even if so what was the relation between this G and N?
Right. So it kind of depends what you start with, right? So so the way that the proof goes is if you start with G, you come up with a stratification. Because G is semi-algebraic, you look at its graph. It's a semi-algebraic set in the product space, and then you stratify Rn in a way that's compatible with that bigger stratification. So the stratification you pull out depends on your particular stratification of G. That would be the way that the argument goes. And a similar thing goes with F, right? If you look at F and you look at its Clarke subdifferential, again, it sits in the product space, and what we show is you can stratify it in a way that you can stratify Rn in a way that makes the graph stratify accordingly. So it sort of comes out of the stratifications of the objects that you've got, but then you could refine it, right? You could throw more points in if you want. So there's no uniqueness in the answer. It just gives you one way of doing it. So.
Okay,
I don't know if that answers your question. Yeah. So there was a question in the chat. Yeah. So so Austin, yeah. So Clarke regular functions and all Lipschitz semi-algebraic continuous functions, they're all path differentiable. Yeah. That is correct. And you know, it's symmetric too. So minus a Clarke regular function is also path differentiable.
Are there any further questions? If not, let's thank Adrian once again for a very interesting talk. Thank you so much.
Great. Thank you very much.